All right, AP review rate is compound nomenclature, and I know in the past couple of years we haven't gotten to spend as much time on this as I would have liked. I'm going to take this one a little bit slower, and if we do need a little bit more time on this in class, we'll definitely touch on it. We are only going to focus on the first two types of compounds, ionic and covalent or molecular. We will talk about learning how to name and write formulas for acids in class. So ionic compounds are formed between metals and nonmetals. They are held together with an ionic bond, the transfer of electrons. They are really good conductors of electricity, whether they are in solution or molten. Solid as alone, they would not be able to conduct because they would not allow the electrons to move. They have extremely high melting points and boiling points. They are very hard, they are rigid, and they are brittle. We tend to see polyatomic ions often in ionic compounds, and I'm going to go point out the list of the ions for the ionic compounds you should know from your summer letter. They are charged molecules that are held together with covalent bonds, and they can replace either metals or nonmetals in your compounds. Although they can be a little crazy to learn, I promise I've cut down this list every year I've taught it. What is nice is that the name and the formula of those polyatomics never changes. I would truly request that you make flashcards of these. If you're having some trouble learning them, it will help you. And we will do some review exercises at the beginning to try to help you with these, but it would be it's going to help you out a lot if you go ahead and start working on learning these sooner versus later. So again, I think that's on page 2 of your summer letter. I already talked about how you want to learn the charges for these monatomic, the single ion, cations, and anions, because without knowing those, writing formulas for ionic compounds is very stressful. These are the polyatomic cations and anions I want you to learn. Again, if you talk to students in previous years, you will know that this list has decreased. I did this a little bit differently than I've done it before. I did kind of keep them grouped together by charges, but more I also grouped them in terms of similarities, hoping that that might help you a little bit. The ones I could anyway. If you notice with the 8s and ites, what they have in common, the nitrate, nitrite, the sulfate, the sulfite, the phosphate, the phosphite, that they all have the same charges, -3, -2, -1, but they just go down by 1 oxygen. Same thing up here with the chlorates. Chlorate and chlorite decrease by 1 oxygen, and then I always say the bookends are the longer ones, the perchlorate and the hypochlorite, 4, 3, 2, and 1 oxygen respectively. Permanganate is very similar to perchlorate, it just has manganese instead of chlorine. With the bicarbonate and carbonate, you're short 1 positive hydrogen, so that's why the charge goes down by 1 with carbonate. Cyanide, C for the cyanide, N for the nide, and as you can tell, most of these have charges of -1. Sulfate and sulfite have the same charge as sulfur. Phosphate and phosphite have the same charge as phosphorus. So I think if you can focus on knowing what the charges are for the ones that are not -1, you can pretty much figure out the other ones because they'll be -1. I hope that helps. I'll try to throw out some other suggestions. Learn these. You're going to use them throughout the year. It will benefit you in the long run. Again, flashcards will be very helpful. Alright, so going back to the review. So when we're writing formulas for ionic compounds, you want to make sure you know the formula's charge. I talked about charges already, how the alkali metals, the group 1s are +1, the alkaline earth metals are +2, and then aluminum and gallium in group 13 are +3, and how the 2 polyatomics, ammonium, NH4 +1, and mercury 1, Hg2 +2, those won't change. And if you have a metal that has a Roman numeral with it, that's telling you the specific charge of that metal. So copper Roman numeral 2 would be Cu +2. With anions, as you get closer to the noble gases, you become less negative. So nitrogen family, group 15 is -3. Group 16, the oxygen family would be -2. Group 17, the halogens would be -1. And we just talked about the polyatomics. You always want to use the fewest of each ion that you need to make a neutral compound. You never want to have your charges show up in the final formula. Every formula should be completely neutral. You just want to show how many of each ion you need to make that neutral formula. And then we use parentheses if we have more than one of a polyatomic ion needed. Alright, so here's 4 names for us: barium chloride, copper 1 oxide, copper 2 oxide, and calcium phosphate. You do not have to do these 2 columns in the middle. If you are okay getting to here with just the names, I'm fine with that. This is just one way to help you kind of keep things organized. Barium is in group 2, so it would have a +2 charge. The ides are always going to come from the periodic table unless they are cyanide or hydroxide. Chloride would come from chlorine, that's in the halogen, so it would be -1. When we cross our charges, chlorine would give barium a 1, barium would give chlorine a 2. So we need 2 chlorines to cancel out the +2 of barium, BaCl2. And if you want to write it as Ba1Cl2, I'm not going to penalize you for that. With copper 1 oxide, again, the copper Roman numeral 1 is telling us the charge of copper. Oxides coming from group 16, so it would have a -2 charge. Across our charges, we would give the 2 to Cu, the 1 to oxygen, and that would give me Cu(2) and an O. So we need 2 +1s to cancel out the -2 of oxygen. In the next example, copper 2 oxide, copper is a +2 ion, oxygen's a -2 ion, again because it's in group 16, it's coming from the periodic table. This time they have the same charge, so if you cross them they would both get 2's, which means you can simplify and just have one of each, CuO. And then the final example here, calcium phosphate. Calcium is in group 2, it's a +2 ion. This time we see we have an 8, which is going to guarantee it's a polyatomic. 8s and ites are always polyatomics. Phosphate is going to be the one with 1 extra oxygen, so PO4 -3. In order to get these charges to balance, we're going to need to cross both. And we're going to need 3 calciums at +2 each to balance out the 2 PO4s at -3. And because we need 2 of the phosphates, we have to put the PO4 in parentheses so we don't show 42 O's. We show 2 PO4s. When we're naming ionic compounds, we want to figure out what our ions are. Our cations are either going to be a metal, or they're going to be a metal with a Roman numeral. We already talked about those a little bit. You have to know which ones get the Roman numerals, or ammonium or mercury 1, the 2 polyatomics. If it is one with the Roman numerals, you got to make sure you use the Roman numeral specifically for it. 1 being I, 2 being double I, 3 being triple I, 4 being IV, 5 being V, and 6 being VI. I think that's as high as you're going to have to go. With the anions, you would name it with ide if it comes from the periodic table for the nonmetals, or you would call it the polyatomics name. So here we have Mg3N2, NH4,3P, SnCO3,2, and SnCO3. I always split these between the cation and the anion. The cation will be a metal or ammonium. That way I've got that taken care of. And then I split the 2 ions apart. The magnesium I know has a +2 charge because it's in group 2. So that's why I put Mg +2. Nitrogen's in group 15, so it has a -3 charge and -3. Because magnesium only has 1 oxidation state, I don't have to do anything more. I just name it magnesium. And nitrogen coming from the periodic table becomes nitride. With the second example, we're splitting it after NH4, which is our cation ammonium. So we would just name it ammonium. Phosphorus is in group 15 along with nitrogen, so it would have a -3 charge. These are binary nonmetals, so we know they're not polyatomics. So it would be ammonium phosphide. Note that the 3 here had nothing to do with the name. That was just to balance out the charges, just like the 3 and 2 up here had nothing to do with the name as well. The only reason those are going to have an effect on the name is if we have a metal, like we see down here at these last 2, that can have more than one oxidation state. Then that will help us determine what is the charge of 10 in those two examples and what Roman numeral 10 should get. So right now 10's a question mark. It could be 2 or 4. While CO3, it's in parentheses, so that's pretty much a dead giveaway. This is a polyatomic. It's carbonate and it has a charge of -2. If we have 2 carbonates in this formula, then we have 2 -2 ions. So that's a total of -4. 10, there's only one of, so 10's charge has to balance out the 2 -2's, which means 10 would have to be +4, so that we would have enough positive charge to balance out the 2 -2's. So when we name it, 10 would get a Roman numeral 4, and CO3 would get its polyatomic name carbonate. And now in our last example here, again, we're going to split it after the 10. We're going to assume we don't know what 10 is just yet, but we know that CO3 is the polyatomic, and even though there aren't parentheses this time, anything after that metal or ammonium has to be a part of the anion. So if we know that SN is our cation, CO3 has to be the anion, and that means it's going to be carbonate. Any little numbers that we see that are not outside of a parentheses have to be part of that polyatomic with subscripts. We have one carbonate ion and we have one 10 ion. If carbonate's -2, to balance it out, 10 would have to be +2. So the only difference between these two names is the Roman numeral 10,2 carbonate. And again, if we need more practice with ionic, I'll definitely give y'all some up on Edline when we return to school. The molecular covalent compounds are the ones you guys tend to like a little bit better because they are a little simpler. They are made from either nonmetals or metalloids. They are held together with covalent bonds because they share electrons. If they're the same elements, they are nonpolar bonds. If they are different, they are polar. They have lower melting and boiling points. They typically are soft and can exist as gases and liquids. Often we see these as binary compounds. Some of the organic ones we will get into later on can be made from more than 2 elements. The roots of these, I don't get too picky about the roots, but you do want to make sure you make a good faith effort. Phosphorus-ide is not a root. You can do phos or phosphor, and I would not penalize you. But you got to make sure you try to get a root at the beginning. And these are the common roots that are used for the nonmetals and the metalloids that we're going to see. And you do need to know those 10 prefixes down there. These are ones you should have seen in a previous chemistry class. If you don't know those, I would make flashcards for them. So when we are dealing with molecular compounds or molecular formulas, we want to write symbols to represent the elements that are being named or vice versa, and then we use the prefixes to determine our subscripts. So I'm going to go both ways with these. We've got triboron hexahydride. So triboron, that's going to come from B for boron, and then the tri would represent 3. Hexahydride would be H, and then we would add on a little 6. And I thought I put the rules in here. Did I miss them somewhere? Hold on 1 second. Yeah, I left those rules out. That's kind of bad. Okay, well then I need to talk a little bit more about this real quick. So with the names of these compounds, the first name is always going to be the full name of the element, and you would use a prefix if there is more than one atom of that element present. With the second part, it's always going to consist of 3 things. You're going to have a prefix, you're going to have a root, and you're going to have the ide added on to each one. So we'll talk about that a little bit more down here. I think with these it's a little more straightforward. Dihydrogen, so H2, and then monoxide would be just the O. Arsenic is AS. Pentabromide, Bro for bromine, and then penta for 5, Br5. So down here when we're naming these, P is going to be phosphorus. Again, we use the full name for the first element, no prefix because there's only one. And then for the second part, Cl3, 3 is tri, Cl would be chlor for chlorine, and then add on the ide, trichloride. With S3, we have sulfur, but we have 3 of them, so trisulfur. and then we would have one O, so mon, and then ox for the oxygen, and then ide. So even though there's only one oxygen, we still need to classify that as being one, so we use mon in front. If you do monooxide, I'm not going to penalize you. Typically, we cut off vowels that are going to add on an extra syllable, and that's just more something you kind of feel over time. It is not something to get too stressed out about. Finally, in the last example, B2, 2 would be di, and then B is boron. Again, full name for the first one. And then F4, 4 is tetra, fluoride. Okay, so with the molecular compounds, hopefully you're seeing that these are all starting with non-metals. And then the only ionic compound that will start with a non-metal would be ammonium. So the biggest thing to watch out for between the molecular compounds and the ionic compounds, if you start with a non-metal, how many elements are in there. If there's just 2, you can feel safe that it's going to be a molecular compound. If there's an NH4 and there's something after that, then you know you're dealing with ionic. These are the common compounds you were asked to learn in Chem 1. You still should be familiar with those. Definitely want you familiar with ammonia and water and hydrogen peroxide and methane. These 3 I'm not so stressed about right now, but I definitely want you to make sure that you're comfortable with those first 4. So on the summer assignment, you should be able to do number 8, or review topic 8. Again, when you're looking for molecular compounds, you're looking for something that's going to start with a non-metal or something that isn't starting with ammonium. So like lithium's a metal, so you know you want to name that with ionic rules. Whereas SO3, that's starting with sulfur. And then you got N2O5 down here, that's starting with nitrogen. Those aren't polyatomics because there's not something else paired with them, so we would want to name those with our molecular rules. If you have any more questions on those, please don't hesitate to ask.